Okay, thanks for the introduction. Thanks to the organisers for inviting me this very long distance. Particularly sort of grateful to be in this environment for the first time and to be part of this workshop, which has such a beautiful title. I'm not sure if I'm a probabilist in any way, and even if I am, I'm not sure if I'm in, on, or of non-Euclidean spaces, but you can decide for yourself. So I'm going to be talking about joint work with a couple of students, Xavier Coulter and Elena Moskovsky, based in New Zealand and Australia respectively. I want to start with a trick. Okay, so here's the trick. You think of a permutation and you call it sigma. And then you think of an integer m, preferably non-negative. And the idea is that we want to do some counting here. So I want to count all the ways I can write this sigma as a product of transpositions, m of them. So let me call it a1, b1, up to am, bm. So you're thinking of a's and b's as positive integers here. And because we're not weirdos, we're always going to write ai less than bi. Okay. Okay, so I want to put some conditions on this. You can, of course, just do that count as you wish, but I'll put some conditions on. So the first thing is I want some sort of connectedness or transitivity condition. I want the transpositions that I'm writing down, these m of them, to generate a transitive subgroup. In other words, to connect all the numbers together. Okay, and so if you do this, what you're calculating are Hurwitz numbers. And this is a long story, dates back, I'm guessing, to the time of Hurwitz in the 1890s, and sort of very much revived over the last 3 decades or so with lots of connections to interesting mathematics and mathematical physics. The next thing I want to do is add in this slightly unusual condition, which is to say that these b's here, b1 through bm, have to be monotone. We want them weakly increasing. Okay, and this is the monotone condition. If you're calculating this, you're calculating a monotone Hurwitz number. And I guess the new ingredient that I want to introduce today is some sort of deformation of this. So when you count like a baby, what you do is you take a set and you put the number 1 next to every element of the set, and then you add up all those numbers. So we're not going to count like babies, we're going to sort of put a little weight on. So the weight for one of these tuples of transpositions is going to be t, so some parameter t, to some power. I'll tell you the power. The power is going to be the number of b's that you see. Of course, you might come along and say, well, Norm, that's just m. No, it's not just m, because these might sort of repeat. We're going to exclude any sort of multiplicities here. Okay, and so if you do this, I guess, I don't know, we thought very hard about a very nice name for this, and we couldn't, so we stuck with our original. These are going to be deformed monotone Hurwitz numbers. Note, they're not numbers. Okay, they're polynomials in T. Okay, and then this little quantity here that we associate to a tuple of transpositions, I'm going to probably use this terminology later on. This is what we call the hive number for obvious reasons. It's the number of bees. Okay. Okay. So here's an example. You might have your own example in your head. So I'm going to take sigma to be 1, 2, 3, 4. If you're not creative enough to think of an example, you can do this. You quickly do the count, everyone. I'll give you 5 seconds. I'll be as generous as Hugo was. And then you probably got the same thing that I did, which is the following. 448 t to the 5 plus 3348 t to the 4 plus 6128 t cubed plus 3348 t squared plus 448 t. And if you did your own version of this, then, surprise, this is the trick, you should have seen some interesting structure. So what did you notice? What do you notice? Yeah, so your polynomial is symmetric in the sense that the first coefficient equals the last, the second equals the second last. I'm not going to call it symmetric just because, of course, symmetric polynomial has other connotations. So I'll call it palindromic. And what else do you notice? Well, you calculated the roots and you realized they were all real. So my claim is that the palindromic is not immediately obvious. In fact, I don't think I have a straight combinatorial proof. I know there are some very sort of avid combinatorialists in the audience. If you don't want to listen to the talk, try and prove this for me. We have sort of other proofs. The real rooted is actually conjecture. I know that your polynomial that you got was real rooted because you probably didn't choose a very big sigma or a very big m, and we've done thousands of computations. Great. But as you know, we're here for probability. And so what is probability about? I guess you could have said that I was doing probability. I just forgot to normalize up there. But I'm actually going to do something which is maybe closer to probability, and that's integration. When you integrate, what do you want to do? Well, you probably need some space to integrate over. You need some functions you want to integrate. You probably need some sort of measure as well. And once you have these in place, you're good to go. The space I want to introduce is something I don't have a very good name for. I'm going to call it S for reasons I don't know, maybe space. And it comes with two integers, capital M, capital N. And if you're wise, you'll choose your m smaller than your n for reasons that we'll soon see. Now, the idea here is, so we want to sort of make up these matrices S. How are we going to make them? We're going to take a, let's say, we're going to take some matrix that's m by n, complex matrix, which is quite nice. I want the rows of this matrix to be orthonormal. So I want some condition like U star, the transpose conjugate, equals the m by m identity matrix. And what's going to happen is my S here is what happens when you multiply U and U star, but the wrong way, so that the answer is difficult. Then you get all sorts of wacky sorts of matrices. They form a big space, and that's my space. You could ask the question, why? The answer is because I said so. But there is some sort of nice sort of geometry to this space, and it turns out, and I think I gave the game away in the title, that this is actually secretly the Grassmannian of m-dimensional, so the space of m-dimensional linear subspace of an n-dimensional complex vector space. Okay. So what are the natural functions here? If I asked you to cook up a function, I want to sort of take one of these matrices, an n by n matrix, and spit out a number, you might think that a nice function is just the matrix elements themselves. So for I and j from 1 up to capital N, you have this function. And it turns out that, as I said, this space is very nice. It's the Grassmannian. This Grassmannian is this nice symmetric, it's a very symmetric object. In particular, it's a homogeneous space. So it comes equipped with this action by conjugation of the unitary group, U of n. And so it turns out that this inherits a nice natural measure, which I'll just abbreviate as ds. What's special about it is that it's invariant under this action of U of n. And because this is a nice compact space, we can normalize this measure so that when we integrate over it, we get the number 1.
So inside J is just coordinates?
Yes, that's right. So here, I and j can be anything from 1 up to capital N. So, and this is usually called a Haar measure. So this is the normalized Haar measure. Okay, and I think the natural question to ask, of course, is what happens when you integrate? So the question we're going to ask today, and hopefully answer, is when you integrate over this space, some product of these functions, let's say si1j1 up to, say you've got k of these guys. I'd like to know, what is this? Oops. If anyone knows how to use 3 boards effectively, let me know. My advisor told me very early on that the best way to use 3 boards is to use 2 boards. I'm getting some nods. Okay, so this wasn't bad advice. Okay, so the sort of question I'm actually asking and answering today comes under the umbrella of what is now known as Weingarten calculus. If you asked me a few years ago what Weingarten calculus was, I wouldn't have been able to tell you. So it's something that's sort of pretty fresh to me, even though the story is reasonably old. Are there people here who do Weingarten calculus? I don't know, maybe? Okay. So maybe I should hand the chalk to you, but I guess I'm here to say something about this. And so this sort of, I guess, people would say, I guess it dates back to Weingarten, probably. Weingarten was a physicist who was trying to calculate integrals in sort of lattice gauge theory. They turned out to be integrals over the unitary groups, and found some sort of nice structure. And this thread was picked up by mathematicians in the early 2000s. And so it has a sort of rich sort of algebraic structure to it. I'm just going to be talking about some sort of very cursory points about Weingarten calculus. Okay, so the idea is that this is a sort of known picture, and I'm looking at some sort of deformation of it. The sort of vanilla version of this picture is something like this. You want to do some integral over the on the group of unitary matrices, n by n unitary matrices, and it turns out, because there's some beautiful underlying structure, that it's very, very closely related to the representation theory of symmetric groups. Okay, so if you show this to someone who's interested in representation theory, they could probably predict that some mechanism underlying this is the sort of Schur-Weil duality between these two sort of representation theories. We're not going to be talking so much about that, and we're going to take a more down-to-earth, hopefully, elementary approach to this. Okay, and so a remark I want to make here is that, you know, a priori, if you've never seen this before, maybe your first instinct is to say something like, let's try and find out what this measure is in some sort of natural coordinates, and let's actually sort of crunch through the computations. Maybe we do this for low m and low n and see how we go. But it turns out there's a beautiful sort of symmetry here and sort of algebra, which means that we don't have to do any of that. Okay, so the first observation is that the U of n invariance sorry. I'll come back to this. I'll come back to that. Okay, so this is where I'm going to make the first error by using the third board, but I believe the trick is to only use it once. Okay. Okay, so there are a few ingredients to Weingarten calculus. You know the sort of integrals I want to calculate here, and it turns out that the first step is to say, well, those integrals with all these sort of indices, which can be whatever they want to be, actually reduce to just elementary ones. And so this usually comes in the form of something called a convolution formula. Okay, so arbitrary integrals of the form written above can be calculated from these so-called elementary ones. And I'll show you how to do it. I won't tell you why though, because it's not sort of the crux of this talk, but the idea is that when you have this complicated series of indices, this reduces to a sum over permutations, and it turns out it reduces to a sum over typically not very many permutations. So you don't typically see all of these k factorial terms here because there are all these deltas that force a lot of these terms to be 0. The idea here is that we're going to sort of permute these I indices to make them match the j indices. Okay. And if they don't match, we don't get any terms. The answer is 0. Okay, so I take I sigma 1 and compare it to j1, all the way up to I sigma k and compare it to jk. And then here I've got some simpler integral where the first term is just 1, the indices are 1 and sigma 1. The next term would be 2 sigma 2 up to k sigma k. And so this is the result. I'm not going to say too much about it because what I'm going to do is concentrate on this thing, this integral over here, these so-called elementary ones. I'll give this a name. So what is this? It just, typically, when you do an integration, you expect some number, but I guess the beauty in sort of these sorts of integrals is that you expect some nice behavior as you vary your m and your n. In particular, this is going to be some nice rational function of m and n. In fact, it's a polynomial in m and rational in capital N. It depends on some sort of input permutation, and that permutation is on k elements here, but k could be anything you like. So I'll call this WG of sigma. That's usually what it's called. WG, I believe, is short for Weingarten.
So why are these elementary and these are not?
Oh, sorry. Elementary, that's my term. Elementary just means I have fewer to think about. So over here I could have like S11, 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 a whole product of those. And in that case you'll get a sum here over all the possible permutations. Okay. Yeah. Thanks for the question. And thank you in advance for any other questions that might follow.
Just to be sure I have understood, for some indices I and j, it might not be that there might not have a permutation so that the right hand side is non-zero.
That's right. And the symmetry forced by the unitary invariance means that you'll get 0. It's a bit like if I asked you, I want to integrate so over the simplest example might be something like over the complex numbers of magnitude 1, I want to integrate just say z over that. There's some sort of symmetry which says it's going to cancel out. Some are going to be positive, some are going to be negative. It just disappears. Okay, and then the next part is to say, well, once we've reduced to these so-called elementary ones, can we calculate them? And there is a way to at least recursively do it. And so what we prove are these so-called orthogonality relations. Okay, and this is what they look like. Say you want to calculate the Weingarten function, this WG, of some permutation that you have fixed in your mind. Then it's related to some other values of the function. So firstly, there's a coefficient here, -1 on n, and then I sum up over these values of I. The Weingarten function evaluated at sigma composed with the transposition ik. All right, so I'm thinking here of sigma living in the symmetric group sk, and somehow k here plays a special role, and I'm summing up over all of these values. That's the first part. There's going to be 3 parts. Okay, the next part is sometimes when you're lucky, your sigma might fix that special number k. Okay, so in that case, when sigma k happens to be k, then this term kicks in. It looks like m over n multiplied by the Weingarten function of take sigma, forget k. That's what that down arrow means. It's a fixed point, just treat it like it's a permutation of just k minus 1 numbers. Okay. So this means forget k. Okay, and then there's a third term as promised, and of course, well, maybe not of course, but you might be able to predict this is what happens when sigma k just doesn't equal k. Okay, and this looks a little bit complicated, but it's not so bad. What I want to do is I want to take sigma, I want to compose that with some transposition. Effectively what I want to do is I want to forget k and its image, sigma k. Okay, so I compose with this sigma inverse of k, and then I can sort of forget. Sorry, what I said before was wrong. What I want is I essentially want to forget k. So if you imagine you write down your permutation in disjoint cycle notation, and you just take the k and you remove it. That's what we're doing. Sorry, that's not even true. It's what I've written, okay. So I want to sort of compose with this to get k back to a fixed point, and then remove k. Okay, and so I want to give these three terms names. I want to call this terms of type A, this one terms of type B, and this one terms of type C for reasons that will hopefully become clearer a little later.
So why is this called the orthogonal relation?
At least in the sort of original sort of unitary case, a proof, maybe not the proof, comes down to just the fact that the rows are orthogonal vectors. So you sort of, it's a sort of manifestation of that. Yeah. It's a little bit more hidden here, yeah. But it does boil, you could say it comes down to the fact that this UU star equals IM, something like that. I can maybe show you a taste of the proof. Sure, let's try it. Okay, these ones are manual? Yes. Okay. Okay, so let's see a taste of the proof. In just this special case, sigma k equals k. So what that means is we're missing this C term here. It's just not there. That's the complicated one, so you can imagine the other half of the proof is slightly more complicated, but not too bad. What I'm going to do is just cook up some mysterious expression, which is a sum of these integrals. So I take S1 sigma 1 up to Sk minus 1 sigma k minus 1. You see, what we're trying to get at here is what happens when you put Sk sigma k here. In other words, skk. But I'm not going to do that. I'm going to write just Si I. And the idea is that for most values of I, this is actually going to be essentially the same. When I is k, we get exactly what we want, right? Wg of sigma. When I is k plus 1, somehow it doesn't affect all these previous terms, and so it's just going to look exactly the same. There's a sort of symmetry when you move, when I is k, or if it's k plus 1, k plus 2, all the way up to n. That's somehow the idea. When it's lower than k, then other terms kick in precisely because of this convolution formula. There's some sort of interactions going on because you've doubled up on indices. Okay, so let's see how this goes. I'm going to try and calculate this in two ways for you. So the first is to say, well, what are we doing? I'll pull this sum in here, and the sum over Sii is just the diagonal entries in my matrix. It's just the trace of the matrix. Okay, so this is S1 sigma 1 up to Sk minus 1 sigma k minus 1, and then the trace of the matrix S. What is the trace of the matrix S? Any guesses? So it turns out that if we sort of look up here, the trace of the matrix S is the trace of UU star, which is the trace of IM, the identity, M by M identity matrix. It's just M, capital M. Okay, so what we see is M here, so this just pulls out. But what is this leftover bit? It's another value of the Weingarten function, not for the same permutation sigma, but for sigma where you've dropped the k bit. So that's precisely what we're calling sigma down arrow. Okay. So this is the first sort of way to compute this. Let's start the computation all over again, but now use the convolution formula. Okay, so I don't know, I find it very combinatorially tricky to use convolution formula. I'm just going to tell you the answer, and then you provide your own reasoning in your head. I think that's actually how we all teach combinatorics typically, right? You say the answer, then everyone provides their own reasoning. So this is what you would get. So I sort of already mentioned that we're going to get two types of behavior here. There's what happens when I is a bit small, in particular smaller than k. And here, what do we want? We somehow want to sort of permute the first indices of the s's to get the second indices. And so you could just take sigma. That one's fine. But you could also, because imagine you had S11 here, that's going to sort of have some interplay with this one over here. And so this is why we get this other term kicking in, where you compose with this transposition that swaps I and k. On the other hand, if I was bigger, whoops, not I, as in I, the index was bigger, then you don't have this second term kicking in. You only have this value of the Weingarten function that you would like. And so putting everything together, how many Weingarten functions of sigma do we get? All together now, it's n, okay? And then we have this leftover term, which is this sum. Okay, let's call this 2. And I guess the final part is, which you can do, is that 1 equals 2. We'll recover the this formula in the case of k being a fixed point of sigma. Any questions?
So just to be entirely sure, k has to be smaller than n?
Yes, yeah. Sorry, this is a standing assumption throughout is that we'll take k to be smaller than n. There are sort of ways to access k larger than n, but we won't worry about that today. And typically we're concerned about large n behavior in these problems. So hopefully that's sort of satisfying enough for you, but you can make sense of these when k is smaller than n as well. But it takes a little bit more care. Yeah, good question. Good omission and good question. Any other questions? Okay, so what you can observe from these orthogonality relations is that they're linear. You just have like some coefficients sitting in front of some values of the Weingarten function, and you can ask, is this enough to actually calculate all values of the Weingarten function? And if so, isn't that great? And the answer is yes, you can calculate everything. And I want to give us a few ways to think about how we do it. One thing you can do is just start actually solving the linear system. Just pop it onto your favorite computer algebra system and solve it for sort of increasing values of k. Work everything out for k equals 1, k equals 2, k equals 3, and you'll observe that you get these nice rational functions of m and n. Maybe it's time to stress, just once again, that a priori, trying to calculate these sorts of integrals, you might not expect that there's a nice uniform behavior as you vary m and n. You know, you're changing your space, hence you're changing your functions, hence you're changing your measure each time. But the somehow beauty of all of this is that, and I guess we know this from sort of many contexts, is that there's a nice uniform behavior as you vary your capital N. Okay, so let's solve these so-called orthogonality relations. Okay, so the next thing I have to do is draw a very complicated picture. So let's see how I go. You see, the Weingarten function takes in permutations, and those permutations can come from symmetric groups of any size. So for instance, you might have, so this, I'll write these in disjoint cycle notation. This is just the identity in S3. And let me write down all the elements of S3. Okay, underneath, sort of this layer down, I'll write down the elements of S2, of which there aren't many, S1, and then let's say S0 for completeness. Now, if you wanted to, say, calculate the value of the Weingarten function for, I don't know, something like this, the transposition that swaps 2 and 3, you might go back to that orthogonality relation and plug in sigma equals that permutation. It's going to relate it to some other things. In particular, I guess that first term means it's related to this thing over here and this thing over here. In particular, you're going to get a term kicking in for when that extra transposition you throw in is 1, 3, and one for when it's 2, 3. And these are both terms of type A. Okay. So what I'm going to do is I'm going to try and record these orthogonality relations in some graph. This is called the Weingarten graph. Okay. So what we get is these terms of type A across the top. Here I'm going to pretend my blackboard is a cylinder. Okay, so these are the type A terms you can have at this level. Now, type B terms, what do? They only kick in when k is a fixed point, right? When 3 is a loner in this disjoint cycle notation. In that case, you can sort of go from here down to here. So this would be something of type B. Observe that we're just sort of forgetting that fixed point. We're not actually sort of doing anything with transpositions, so I'm not going to record any transposition on B arrows. On the other hand, if you looked at something like this transposition 2, 3 here, this one you can get down to here by doing a type C term, and that type C term picks up, type C terms have a transposition. I'm going to write down what the transposition is. Okay. Hopefully you understand the idea. I could draw the whole thing out. In fact, I probably will. But it gets a little bit messy, that's all. we had a few debates about how to sort of draw this in our paper. I won, so this is, this is how we drew it, sort of geometrically. And then I guess I'll add in some extra little labels here, and I haven't put in all the transpositions, but hopefully you understand the idea. Okay, so what do we want to do with this? I guess I want to say that if you want to calculate the Weingarten function for anything here, you can say, well, this is related to this one, but then you get a cost. That coefficient for an A-type move is -1 on n. But you also get sort of m on n, sorry, you also get 1 on n times going down this C arrow. But then you have to work out those Weingarten functions as well. But then you have this sort of inductive sort of technique. But what you can see, hopefully, is that to work out the Weingarten function of anything, you can just take all the paths which end up at the bottom. The arrows only ever go sideways or to the bottom. Okay. And so, let me pop it in here. Here's the fact. If you want to know the Weingarten function for some permutation, you take a sum over all the paths from your permutation all the way to the empty permutation in this Weingarten graph. There's a cost for every time you use an A-edge. That cost is called -1 on n. There's a cost every time you use a B-edge, which is m on n. And there's a cost every time you use a C-edge. Okay, so think about starting at your favorite permutation and doing this in all the possible ways. And there will be infinitely many ways, typically, because you can sort of just go back and forth as many times as you like, and then wiggle your way down. One thing you could do is you could try and say, well, on my way down, I'm going to record all of the transpositions that I see. They only come when you cross an A edge or you traverse a C edge. And so what you end up getting is this long list of transpositions. And it turns out that just by construction, the product of those transpositions is your original permutation. Furthermore, there's this monotonicity condition built into the picture because you basically have to sort of do things which, let's say if you start on level 3, you have to do things which use the 3 first, and then do things that use the 2 as the bigger element, then things that use, well, nothing uses the 1, and so forth. And it turns out what you actually get when you record the transpositions in order is the inverse of your permutation. And so this precisely encodes the monotonicity constraint that I spoke about in the trick that we performed at the top of the talk. Okay, so thinking about things via these tuples of transpositions, you get something like this. You see that, for instance, I want to sort of point out things like this, like, to get from here to here, you could have gone directly via a C, but every time you used a C, you could have used an A and a B. Okay. And so what I want to do is somehow amalgamate things which just use the same transpositions. And so this is the end result. So you get some prefactor, m on n to the, I guess, the k or the level, the number of things that sigma permutes. Then I'm going to sum over all the lengths of the walks, sorry, not the lengths of the walks, by the number of transpositions that I meet when I do these walks. Each transposition, I'm going to give some weight, -1 on n, and I want to know what's left over. What's the coefficient here? And it turns out to be almost precisely the thing that we calculated in the trick at the top of the lecture. It's the number of length m monotone factorizations of sigma with weight, counted with weight t to the hive number. Recall the Hive number is the number of bees. Okay, that doesn't make any sense at all, because what's T? So I need to tell you what T is, and secretly T equals 1 minus n on m, which I think is probably hard to predict, but it just happens to be this by virtue of our setup. Finally, there's a beautiful connection to the representation theory of symmetric groups. And you can sort of predict that something nice is going to happen for a couple of reasons. One is that there's this, which I sort of didn't say it explicitly, but when you have this unitary invariance of the Haar measure, a consequence of that is that the Weingarten function is conjugation invariant, right? So the Weingarten function only depends on the cycle type of your permutation. And anytime you have some conjugation invariant natural function on a symmetric group, it usually has something to do with the representation theory of the symmetric group. So let me write down how you can calculate the Weingarten function using that. It turns out that it's a calculation in the symmetric group algebra. What you do is you write down, so sigma is in symmetric group SK, and I want to write down this product. Here, this J is this beautiful sort of element of the symmetric group algebra called the Eustace-Murphy element. So Ji is what happens when you add up 1i, the transposition, with 2i all the way up to I minus 1i. So the Eustace-Murphy element. So you do that, you're going to get some sort of linear combination of permutations, and then you just extract the coefficient that you want. Okay. So I guess what we see is that sort of integration on these sort of very nice spaces, which secretly Grassmannians, gives rise to essentially the enumerative problem of calculating these Hurwitz numbers, but with this monotonicity and this weird weight, this deformation, t to the power of the Hive number. I want to say something now about these numbers, or these polynomials that we get, in particular looping back to the original trick. Deformed monotone Hurwitz numbers. Okay, so typically these are described using some slightly different data where, as I said, the Weingarten function doesn't depend on the actual permutation, but just on its cycle type. So these are the, let's record just the cycle lengths of sigma. And then I'm going to throw in a G here, which somehow secretly records the m, the number of transpositions. So this is the count of length m, where m depends on g in this following wacky way. And now I want to include this transitivity. It's somehow not a difficult thing to pass from adding the transitive condition or removing the transitive condition. But the transitive one is nicer for me. So monotone factorizations of sigma, and again we'll use this weight. Oops. T to the Hive number. Okay, I just wanted to introduce that so I could state some facts. So the first is that if you look at the most basic instance of this problem, where you set g to be 0, n to be 1, that means you just have a single cycle, a full cycle, then this is sort of a known sequence of polynomials. This is the sequence of Narayana polynomials, but with a little shift in the index. And the Narayana polynomials are somehow some refinement of the Catalan numbers. Okay. I'll also point out that there are various ways to actually explicitly compute these rather effectively. So we've got various recursions. So one is this sort of cut join, or also a topological recursion. Computes these. And it does it rather effectively. So you can just pop this on the computer and just calculate to your heart's desire. And then, as we said previously, these are polynomials with beautiful structure. And in particular, they're always palindromic. So that's the known part of it. And then somehow there's an unknown part, the conjectures, which I invite anyone to help prove. So we've already said that these should be real-rooted, and they are in the many thousands of examples I've calculated. But there's something much richer that I want to point out about these real-rooted polynomials. When you see real-rooted polynomials, what you can do is you can plot the roots on the real number line. And the sort of gist of it is that if you take one of these polynomials, right, say with, I don't know, degree 4, and then you take the next one up, whatever that means, I'll say in a second, with degree 5, the roots interlace along the real number line. They alternate. Okay. This is completely observational and empirical. Okay, so you take this polynomial and its roots interlace. The next one up, what do I mean by the next one up? It means you choose your favourite index in here, mu I, and bump it up by 1. Okay. So this is some sort of phenomenon that's commonly studied for sequences of polynomials. Here we somehow see sort of a lattice of interlacing. Once you fix your G, you see a lattice of interlacing, n-dimensional lattice. I don't actually know how to prove this at all. So I'd be quite interested if anyone thought that this was obvious or had some natural approaches.
Some topological interpretation of the monotonicity condition in the hive number.
Topological? I'm not sure. It's a good question. Yeah, it's a question that people commonly ask. So these sort of factorizations, intertranspositions commonly relate to branched covers of surfaces. The transitivity, of course, is some connectedness, but then the monotone is not an easy thing to incorporate. There are other, maybe more diagrammatic ways to think about it that maybe are closer to topology, but I've never found them particularly useful, at least for me. Yeah. What does the weight mean? I'm not sure. Yeah, there are good questions there. Maybe I'll just use up. I have 1 more minute. I might use up 1.5, if that's okay. Just to speak about topological recursion, because essentially that was in the abstract, and I haven't really mentioned it explicitly yet. What is topological recursion? Basically, when topological recursion started, everyone would always write down the formula. It'd take you about 15 minutes, which I don't have. So to me, topological recursion is some sort of box where you feed in something called a spectral curve, and you get out something called a partition function. And I'll show you an example, if I have the time. Function. Okay, and a spectral curve in some sense stores, in many examples, what I'd call the disk enumeration. Somehow, it solves the problem of you have a disk and you sort of have some positive integer mu and you have some problem there. Whereas over this slide, what you get out is all possible topologies. So in other words, you might have some sort of crazier surface, and then each sort of boundary component is endowed with some positive integer. Loosely speaking, topological recursion is going to do that for us. So it takes the data of the Narayana polynomials in this case and produces every single instantiation of this problem. Okay, and so I guess the fact is that if you try and sort of work out what happens when g equals 0, n equals 1, when g equals 0, n equals 1, you can write the generating function the following way. Y of x equals the sum h0, 1 of mu. I set that next to x to the mu minus 1. And it turns out that this actually comes from an algebraic curve. The algebraic curve being x, y squared plus t minus 1, t being the parameter, the deformation parameter here, oops, minus y plus 1 equals 0. And the idea is you feed that, this is the spectral curve, you feed this into topological recursion, and you get out all possible numbers. And in general, topological recursion is a really valuable tool, I think, for sort of finding analogies between what initially look like very distinct problems. And I just want to sort of maybe solve that with another conjecture. Just if you've sort of been through sort of this whole sort of story, you can sort of look for it in other places. And I just want to give you one instance of it. So I'm going to sort of define a similar problem. There's a g, and there are n positive integers, mu1 through mu n. And this is a combinatorial problem of counting genus G connected descendants, or in other words, bicolored maps with so the vertices are colored in black or white. Black vertices of degrees given by the mu's with weight t to the number of white vertices. Okay. And I guess the conjecture is that the sort of here the palindromicity of the polynomials we get is immediately obvious by, am I saying this correctly? Immediately obvious by exchanging black and white vertices. But the real rootedness has been observed in thousands of cases, but I can't explain it. And similarly, the interlacing. Okay, so this is not just some contrived sort of isolated phenomenon. It could be two contrived isolated phenomena, but I predict that there's probably more, and there's probably more to this story, and I'll finish there. Thanks.
Okay, thank you very much. Are there any questions?
Does the palindromicity generalize to more general weighted Hurwitz numbers? For example, if instead of one monotone run, you take a fixed number of monotone runs? Or some version of it, like some symmetries.
Yeah, that's not something I've thought about. So the short answer is I don't know. It's definitely sort of, yeah, there are other more general versions of this story for which you could ask the same sorts of questions. I don't know. I absolutely don't know. Thanks.
And what about the beta deformations?
What do you mean by beta deformation? So you can run this story, for instance, for the orthogonal case, which I have a couple of students working on.
Do you have palindromic words in this case?
Yes. So palindromic, real rooted, interlacing. Yep, in type B. Conjecturally.
Hey, so you have a nice formula with juices, Murphys, and all. Do you get can you like collect all your numbers into a solution of KP, maybe?
Yes. So this should give you a one-parameter deformation of a KP solution for monotone Hurwitz numbers. Yes, absolutely. So the all the connections to topological recursion and KP are somehow known things. Once you get into this, as you've already sort of predicted, once you get into this Eustace-Murphy form. Thanks.
All right, any other questions or remarks? Okay, if not, let's thank Normando again.